Hi, we are Group 4 and this is our presentation.
Hi, I'm Kang. I will be presenting the introduction part. Our group has chosen to design an 80 mega 328P based temperature monitoring system. It is based on AVR RISC architecture. It has 38 I/O pins, each with different functions. It has ample program and data memory. It provides a 6 channels 10-bit resolution ADC module. The LM35 temperature sensor is highly accurate and simple. The relationship between the voltage measured and the actual temperature is linearly proportional with a factor of 10 mW per degree Celsius. The sensor does not need external calibration. The amount of current used is less than 60 microampere, which reduces the issue of self-heating. The 16x2 LCD display has a compact size with adequate display area. The display is easy to use as they are widely supported and have example code. The displays consume minimal power and has a standard interface which allows for easy compatibility. The system involves the integration of all three components as mentioned earlier. The input interface involves the conversion of analog readings from sensor to digital values in the microprocessor, with proper initialization of pins. The analog voltage outputs are read and converted into digital values using the built-in ADC. During data processing, the digital data needs to be converted to useful information such as temperature, using the conversion factor given. The temperature data can be used in control algorithms to regulate a system's temperature. The output stage of the system utilizes various devices to present the process data. The LCD display enables users to obtain real-time temperature data. Additional components such as actuators can be used. For example, a LED and a buzzer can be used to alert the user if the detected temperature has exceeded the threshold based on the process temperature data. That's all from me. Thank you.
Hi, I'm Keat and I'll be talking about the input interface for our project. We choose ADC specifically and A0 channel for collecting the data from the LM35 temperature sensor. The table here shows the connections of the sensor to the UNO pin and the corresponding ATmega 328P pin. Before the configuration of ATmega 328P, we must understand the key register need for the ADC configuration. First one is the ADC SRA register, which helps in enabling, starting the conversions and also setting the prescaler value. Then the MX register helps in setting the reference voltage and the input channel selection. Last one is the ADC result register that store the ADC results of the ADC conversions. Now we're configuring the 328P. There are two main sections, which are ADC initialization, which highlighted in blue here, and the ADC conversion, which is highlighted in pink. I'll explain in the general steps for the configurations. In the initialization, we first set the reference voltage to 5V in the MX register. Then we enable the ADC module and set the prescaler value to 128 in the ADC SRA register to have the ADC clock frequency at the 125 kHz. In the ADC conversions, we first must select the correct input channel, which is ADC 0 in the MX register. Then we start the conversions by setting the ADC SRA register. We wait for the conversions to be complete by checking the ADSC bit using a polling loop. Once the conversion is finished, the ADC result is stored in the ADC result register. So after coding, we simulate it using the ML Studio to obtain some time information. So from the simulation that we did just now, we can see that the stopwatch showing 168 microseconds. If we simply do some calculations, we can obtain the actual sampling rates under the configurations of the 125 kHz. The ADC clock frequency will be 5.95 kHz. So theoretically, the maximum sampling rate under the similar configurations will reach up to 9.6 kHz actually. So for the extreme case, which in no prescaler setting is done, the maximum ADC sampling rates that the 328P can handle is at 15 kHz. So we also obtain some information about the total clock cycle per ADC conversions, which is at 21 clocks per conversion.
Hi, I'm Singri. Now I would like to proceed to talk about the data processing process. During data processing, ATmega 328P carries out operation on the received LM35 sensor data. The code of data processing is shown in this slide. Now we move on to the explanation of the code related to data processing. During the initialization process, the analog input pin A1 of Arduino board is connected to the LM35 sensor to read the analog voltage output. Next, in the setup function, the serial communication is initialized with a baud rate of 9600. This allows communication with the Arduino board and viewing the temperature values on a serial monitor. Next, the analog read function is called to read the analog voltage value from pin A1 and store it in temperature ADC value. The digital value obtained from analog read is then multiplied by 5 and divided by 1023 to convert the ADC value back into the equivalent voltage. The resulting values are stored in temperature value, representing the voltage value of the LM35 sensor output. Lastly, since the LM35 sensor has a sensitivity of 10 millivolts per degree Celsius, multiplying the voltage value by 100 converts the voltage value in millivolts into temperature units in degrees Celsius. After the coding, we simulate it using ML Studio to obtain some timing information as shown in this short video. From the simulation of ML Studios, the total clock cycles obtained to complete data processing is 6106 cycles as shown here, while the MICROCOMPUTER and Arduino board is assumed to run at a clock frequency of 16 MHz. Hence, the total time taken to complete data processing calculated is 0.38 millisecond, which is the same as stopwatch timing as shown in the processor status. There are several methods to improve data processing. One of the methods is optimizing the algorithm by exploring alternative algorithms that can achieve the same results more efficiently. Besides, lookup tables can also be utilized to perform complex calculations or functions, which will reduce the computation time. Another method to improve data processing is to optimize memory usage. Unnecessary data such as null values and duplicates should be removed to ensure efficient utilization of memory resources. In addition, microcontrollers which are more powerful with higher clock frequencies or specialized processing units should be used. Moreover, interrupts should also be utilized to handle time-critical operations or external signals, which allows the microcontroller to respond quickly and efficiently.
I'm Kelly and I'll talk about the output data rate then. So first, data rate is defined by the rate of data that can be transmitted to the output pins, as the default clock frequency of MICROCOMPUTER are 60 MHz and the configuration are 8 bit, which the total number of bits per character are 10, including one party bit and one stop bit. The current output data rate can be calculated using the baud rate over the number of bits per character. So for our case, we have chosen 9600 baud and it will produce 960 characters of data per second. So maximum baud rate for MICROCOMPUTER is 115200, so the maximum data rate will be 11520 characters of data per second. There are also several factors that will affect the output data rate. Data rate is the microprocessor clock speed, memory, microprocessor processing power, progress complexity, and I/O pin restriction. After we have a general idea about the output data rate, the figure in the table below shows the connection between the MICROCOMPUTER to our output interface, which is the LCD. So in the LCD, the RW shows the read-write pin, E for the enable pin, and RS is for the register select pin. The function of this pin will be explained in the Arduino coding at the next one. Next, I'll present about the Arduino coding of the system for output interface. So the first line indicates that we have declared D4, D5, D6, and D7 as our data line. So the D4 and D5 are representing port 6, while D6 and D7 are representing port D. We are comparing it with the figure below. So it also shows that we only use 4-bit data transmission instead of the default 8-bit, and the data is then transmitted to the LCD module in two distinct 4-bit niveaus. For upper nibble command, port C is being used, which the RS is written to 0 and the EN is written to 1. ENP will toggle to 0 and be ready to send the lower nibble of command by repeating the process above. Next, LCD begin 16.2 shows the initialization of LCD module to add MICROCOMPUTER. It involves 5 steps, which are return home, function set, display on off, entry mode, and clear display. The number of columns are declared to 16 and the number of rows are declared to 2 to be printed. These processes are replaced by the liquid crystal H library in the Arduino code. So next, serial begin 9600 shows the serial communication between the LCD and the MICROCOMPUTER, which the baud rate is set to 9600. Next, for the LCD set cursor 0, 0, it shows the address of the first line is 0 multiply 80, while the address for the second line is 0 multiply CO. So for the LCD print, it will transfer the data and print it on the LCD display. Data will be converted to string before it is transferred, and to write the upper nibble of data, the RS pin are toggled to 1 as well as EN pin. To write the first line data, and they will be toggled to 0 once the data are completed set. So finally, for the delay 500, it shows that we actually established a 500 milliseconds delay in the system. Next, by replacing the Arduino code into the ML Studio, it shows the simulation of the timing information, and the video will show the process of the simulation. From the video, by step overing every line of the Arduino code, we can obtain the final cycle counter for the system are 96951. By letting the clock frequency to 16 MHz, the total time taken can be calculated using the total clock cycles over the clock frequency, which the total time taken for the output data will be 6.059 milliseconds.
I am Yi Xun, so we have our simulate here. First, we need to insert all the components. Since we don't have the ATmega 328P, we use 328 as they are quite similar. For LM35 sensor, we use the voltage source by limiting 1.5 volt as the maximum voltage based on our topic. Connect all the pins and we need to load the firmware. To do this, we need to use the hex file and it can be found using Arduino. To load the hex file, switch on and the simulation is completed. If you notice, on 1.5 volt, the temperature will be 149.56 degrees Celsius instead of 150 degrees Celsius. This is because Arduino can only process integer. Also, there are some improvements that can be done. We can use the assemble language. It only requires a small amount of memory compared to C programming. Besides that, this language has smaller codes resulting in faster operation, which is more suitable for our program. We can change the sampling rate of the clock frequency to a slower cycle. We might not require a high sampling rate of clock frequency in our case, so it can be adjusted to a lower to save the power consumption. We can also improve the program by having a sleep mode in between the previous and next operation. By doing so, power usage can be optimized, but it won't affect the normal operation of the program. We can take multiple readings in a period of time and average of the reading is calculated to reduce the effect of random noise and improve the accuracy. That's all from us. Thank you.